Rasterization is the most common way computers display images on a screen. These images are translated into a 2D grid of pixels and the shape is defined using vectors for the computer to understand. The colors are calculated outside of this and are handed in when a pixel is needed to be drawn. We start off simple, triangles. We look for our 3 points defining our corners and arrange them in height order. We then start filling the rows in line by line from the bottom up, effectively rasterizing our triangle. But there's a better way to do this with something called barycentric coordinates. This effectively optimizes the way we rasterize. We construct a bounding box around each triangle we're drawing, and by doing this we can ignore every pixel outside of it. Checking if a point is within a triangle or not is another vital step. We know that it is in the triangle by checking the point is not beyond the edges. That is, that all 3 checks are above 0. A TGA class was given to us conveniently to produce TGA files to visualize the results of rasterizing triangles. Using an image set color, we were able to color pixels to this image. Backface culling is a technique whereby faces are not visible to the camera and are not drawn, and is achieved by using the vertex normals calculated in ViewSpace. This optimizes the rasterization process because we skip drawing triangles. This is achieved by getting the dot product between the face and the camera direction. Writing a custom matrix in Vector4 class to handle positions and perspective. A perspective camera was implemented to position and implement the scene. A perspective camera requires a pipeline of steps to correctly give the illusion of perspective on a 2D screen. The pipeline is model to world space, world to camera space, camera to clip space, and finally we do a perspective projection and perspective division to map them to the screen. Like vertex normals, OBJ files contain a UV mapping that allows color sampling to apply textures to a model. First we get the locations from the OBJ files so that we can get the right sampling locations, and then a texture is loaded in to sample from. Apart from simple texturing, HDR support was added. This is a higher precision color interpolation with floating point values to allow better color representation in the image. Reinhardt tone mapping is required to put these values back into a 0 to 255 range, as well as gamma correction is needed, else the image becomes too overexposed. Z-buffer face removal is a simple concept where faces that are behind others should be overwritten with ones that are in front. Each model uses the same shared depth buffer so that all Z locations are known and can be appropriately updated. Each pixel location is checked in the buffer and the ones the closest to the camera are shown. Anti-aliasing is a way to smooth out rasterized results by removing jaggies. The way this is done here is through supersampling. This is the processing of an image at a higher resolution and then reducing an image back to a smaller resolution and then averaging the mixed pixel colors, creating a smoother edge. The image rasterized starts at a 4K resolution and then is downsampled back to an HD resolution. Doing it this way stops the need to upscaling first. Reading and models and drawing to TGA image use a common class that is both used in the rasterizer and ray tracer. This gets the OBJ information such as vertices, normals and UVs, while the TGA image allows the creation of an image comprised of RGBA values. We use a vector to represent a ray that is output through the camera and into the scene. Rays are comprised of an origin and direction and are used to describe the path of light in scene. Using a hit info struct and an intersection text, recursion is used to modify our color along the ray until it reaches its last location. Eigen was standardized for the use of a vector utility, as well as having the benefit of using them to represent RGB color values as well. The Moller-Trumbo algorithm is used to define triangle intersections. This algorithm uses a system of linear equations and barycentric coordinates to compute successful intersections with triangles. A perspective camera is implied when ray tracing, unlike a rasterizer, because rays define the attributes of each pixel and the direction those rays are cast and bounced. The relationship between these attributes simulates how light would work entering a lens, giving depth and perspective. Making a spotlight from the ray tracer was a fairly straightforward procedure. By taking the point light system given, all that was needed was to define a direction that the spotlight would be pointing towards, as well as an angle to define the light cone. Some attenuation is also needed to define the fall-off of the light around the edges, as well as the further away it is from the source. A metal shader was created by building off a given mirror shader. Sharing similar properties, a roughness and albedo were added by using an in-unit hemisphere to randomizing incoming rays with a radius around the surface normal, and a roughness to define how much deviation there will be. We can create a simple version of subsurface scatter using only the roughness value. It was further extended to support a textured version of this metal material. A dielectric material was added to the ray tracer by the use of refraction. This is what variation the ray will differ through a given material based on its refractive index. These materials represent glass, water, and even air. Similar to the rasterizer, to get a smooth image we need more samples to work with. To do this, stratified jitter was used to sample random pixels around the current sample and averaging them. Modifying the getRay function, a random offset is added to the inner loop and averaged for every ray. This increases the rendering time significantly for a better overall image. Depth of field is also fairly straightforward. The camera class is enhanced by defining an infinitely small lens in front of the camera, and this augments the passing rays to converge at a given distance. We define this lens as a circle so that points are able to converge and simulate focus. Then in the getRay function, distortion is added to anything out of focus and increase the focus as objects fall into the focus range. Aperture defines how wide the focus area is, and the distance defines where the focus is the sharpest. Let's speed it up with the bounding volume hierarchy. This is where access aligned bounding boxes are used to define when a ray needs to be considered for a test, and a BVH defines these boxes in a hierarchical tree that takes smaller and smaller areas, effectively reducing the time needed to test a ray or not. This can be done over a whole scene and on individual models, making the process faster by reducing unnecessary tests. Using Blender and a PBRT plugin, the goal was to recreate a scene from Stray. Physically based rendering supplies advanced rendering techniques to simulate properties of real objects in the virtual space. Diffuse dielectric and emissive materials were used throughout the scene, as well as textures, normal maps, and roughness maps. Due to the game being copyright, accurate textures and assets were not available.